Good morning, everyone. The first talk in the morning section is given by Professor Weinkove from Northwestern University, and his title is Partial Differential Equations and Convexity. So let's welcome.
Wait. Oh, okay. Okay, let me start again. I hope that you can hear me a bit better now. So I'm going to talk about partial differential equations and convexity, and in particular I'm going to be talking about evolution equations and notions of convexity that are preserved in time. So I'm going to begin with an equation that we're all familiar with, the heat equation, and give a brief introduction. And then in my talk, I'm going to discuss three equations. All of those equations are coming from physical processes, and they all have the feature that they have a free boundary. The first equation I'm going to talk about is the porous medium equation. This is a classical equation modeling the diffusion of gas. The second equation I'm going to talk about is the so-called Stefan problem. And this is an equation which is used to model the melting of ice. Again, it's rather classical. The third equation I want to talk about, again, involves a free boundary. Is less well known. It's called the quasi-static droplet model, and it's something that models the shape of a liquid droplet. And then I'm going to give you some sketches of proofs. What I'm going to talk about today is some joint work with Albert Chow, and actually we construct some examples. And we'll see that the proofs are actually very elementary. Okay, so let me begin with introduction. And as I said, I want to talk about the heat equation, which is something that I think we're all familiar with. So in Rn, the fundamental solution of the heat equation, so heat equation du dt is Laplacian of u, is given by this formula that u of xt is 1 over 4 pi t to the n over 2, and then e to the minus x squared over 4t. So for any fixed t, so take t equals 1, it's just e to the minus x squared, essentially. You get this Gaussian distribution. This is supposed to represent the temperature. What happens over time? Well, as t increases, of course, the heat diffuses, and so the curve flattens. If you go backwards in time to t is 0, all of the heat is going to concentrate at the origin. And indeed, if you take a convergence in the sense of measures, you'll get convergence to a direct delta measure at the origin. So this is a talk about convexity and concavity, and you may notice that this function is neither convex nor concave. And indeed, any function which is positive and is decaying at infinity is not going to be globally convex or concave. On the other hand, we can take the log of this function, and we get minus log of 4 pi t to the n over 2 minus x squared over 4t. And then if I think of this as just fixed t and think of this as a function of x, it's just minus x squared, essentially. And so this is a concave function in x. So we see that the heat, this fundamental solution satisfies the condition that its log is concave, and we say that u is log concave. And then a rather classic result, going back almost 50 years, by Braskamp and Lieb, says that if you start any initial data. So here my U is not this fundamental solution, but my U is just any initial data, which is positive and its log is concave. Then for later time, the function x goes to U of xt is also going to be log concave. And so we say that log concavity is preserved by the heat equation. And so this provides a motivation for my talk. And I want to ask the question of, for other evolution type equations, do we see the same kind of preservation of convexity or concavity? I come from a background more in geometric analysis. We see that a lot in geometric problems. Often in there, convexity takes on the role of curvature. And we see that it plays an important role to ask whether these things, positivity is preserved. Here, I'm going to be looking at some, as I said, some problems involving free boundaries. And the first equation I want to look at is the porous medium equation. And as I said, this is, I'll abbreviate this as PME. And as I said, this models the diffusion of gas, and it's an equation that goes back to the 19th century. If I write U of xt for the density of gas at a point x in Rn at some time, so of course, since it's a density, it's bigger than or equal to 0, then the porous medium equation says that du dt is Laplacian of u to the m. Now, what is m? M is just a fixed constant, which is strictly larger than 1. So, of course, if m were equal to 1, this would just be the heat equation. This is sometimes called the nonlinear heat equation. With this power m, this makes it into a very nonlinear equation indeed. I suppose I have some initial data, let me call it u0, and I'll call this equation the porous medium equation, or PME. Okay, so let me say a little bit about this equation. So we're going to assume that my initial data is going to be compactly supported. So I'm drawing it an example here, and I'm going to be dealing with cases where the initial data is going to be smooth on its support, but it's not going to be globally smooth. And you can see that where I've drawn it there, the derivative, well, we have a corner here, so the derivative is not even going to be continuous at the boundary. So in general, you're not going to expect more like some kind of C gamma global bound initially. And indeed, when you're dealing with the porous medium equation, you always are going to have to be dealing with singularities of the derivative. It's just a general feature if you want to think of the function globally. So what do we expect? Well, we expect if this is some distribution of gas, you expect the gas to spread out over time. And indeed, this is exactly what happens. Now, the porous medium equation is a degenerate parabolic equation. If you write out what it is, so Laplacian of u to the m has two terms. You get m u to the minus 1, and then Laplacian of u, and then plus this first order term, m minus 1, u to the m minus 2 gradient of u squared. And what you notice is that when you're on the boundary of this set, where u is 0, then the principal term on the right-hand side involving the Laplacian is going to vanish. You have a u to the m minus 1, but this u is going to vanish. And that's what makes this degenerate, and that's what makes this equation so interesting. We're going to write capital omega of t for the set where u is positive. In other words, this is the set where there is gas, where the gas is. And it's a general fact, coming from the fact that this is a nice parabolic equation where u is positive, that as long as you're in some positive time, u is smooth on capital omega t for t positive. If you're interested in global regularity, there's work of Caffarelli and Friedman from the 80s, which says that it's going to be globally Holder continuous on Rn. In fact, there's some interesting open problems there about what the optimal Holder exponent is. If that's still open problem there, that's not something I'm going to worry about in this talk. Okay. So this is the equation I'm looking at, the porous medium equation. And I'm going to assume, for the sake of this talk, that m is equal to 2. It turns out that the theory that I'm going to talk, all the results I'm going to talk about are insensitive to the particular value of m. And there's some advantage in taking the constant m to be equal to 2. if you want to deal with general M bigger than 1, the standard thing is to make a change of variable, and rather than work with the density, we work with something called the pressure, and the pressure is usually written V, and it's U to the M minus 1, and you'll notice that when M equals 2, then you have this coincidence, the pressure is the same as density, and that's going to simplify things a little bit for us. What you'll see is that a lot of the results I'll talk about will actually, in general, be holding for pressure rather than for density, but we're in the case where density and pressure are the same. So we talked about the fundamental solution of the heat equation. Well, what's the fundamental solution of the porous medium equation? So this is called the Barenblatt solution. It's also called the ZKB solution. And it's written as follows. So here, A is a constant, a positive constant. So we have a family of solutions. They can have different masses. So the larger A is, the more gas there is. So you can ignore these particular exponents, and this coefficient is not that important. What you see is that really this is just a constant minus another constant times x squared. And then with this plus, I'm just taking the maximum of that function in 0. In other words, as soon as this quadratic is negative, I just take it to be 0. So we get something like this. So for any fixed t equals 1 or something, it's just a constant minus x squared, and then I just cut it off when it gets negative. So this is this is going to be my fundamental solution. So let me say a little bit more about that. So one thing you notice is that as t increases, it's not difficult to see that, as you would expect, the gas is spreading out as t increases. And as you go backwards in time, it's focusing at the origin just in the same way that the fundamental solution of the heat equation did. And again, if you were to talk about convergence in the sense of measures, then you get convergence to a Dirac delta at 0. If you took general M, here I wrote down the solution for M equals 2. If you wrote down the solution for general M, you would have some power 1 over M minus 1, and you would have some M's occurring in the constants. It's then an exercise to show that as M converges to 1, this solution will actually converge to the fundamental solution of the heat equation. Okay. So this is the Barenblatt solution. Let me remind you again what the formula is. And this is the set which we call capital omega T, where there is gas. And this is the set, it's just a ball, and x squared is less than or equal to this quantity, which depends on t. And you see that as t goes to infinity, this tends to infinity, so it spreads out. So this is the Barenblatt solution. So let me make a few remarks about this solution and also about the porous medium equation in general. So interesting feature of the porous medium equation is that it has finite speed of propagation. So you see that this solution is moving with some finite speed. You can certainly calculate the speed of that boundary of that solution very easily. This contrasts with the heat equation. The heat equation famously has infinite speed of propagation. It satisfies a strong maximum principle. So with the heat equation, if there's a little bit of heat somewhere, it's immediately positive everywhere. If there's a little bit of heat at one side of the room, I feel some positive heat at any positive time. That's not true for the porous medium equation. Oops, sorry. So for example, suppose I'm in a room and there's some distribution of poisonous gas, and I wanted to know how long I have until my demise. Well, I can come up with a lower bound for that using what's called the avoidance principle or comparison principle, because the porous medium equation, like many parabolic type equations, satisfies a comparison principle. If you have one solution that's above another, it will stay in that order as time evolves. So you could draw a Barenblatt solution over the top, and then that poisonous gas will remain below this Barenblatt solution. You can estimate how long you have left. It turns out that all solutions to the porous medium equation, at least if they're compactly supported, are eventually asymptotic to a Barenblatt solution. The sharpest result there is proved by Lee and Vasquez. And so it doesn't matter, even if your support is disconnected, looks a little bit crazy. Eventually, all this gas is going to come together, the support is going to approach a ball, and the solution will be asymptotic to a Barenblatt solution. And we're talking about convexity. And so what you notice is that this solution, it's just like minus x squared. So it's concave. at least it's concave on its support. Of course, it's not concave as a function on Rn, but it's concave on its support. And when I'm going to talk about concavity, I'm going to be talking about concavity on the support for every T positive. And so there's a natural question to ask, which was asked back in the 80s, is concavity of U preserved along the porous medium equation? So this is the question we're interested in. And just remind you, we're taking m equals 2, so this is what the porous medium equation is. It's just ut is Laplacian of u squared. So the first result in this direction is proved by Benelin and Vasquez in 87, and they showed the answer is yes for dimension 1. It turns out dimension 1 is a little bit special. In this case, the boundary is just going to be points. Different things happen in higher dimensions that you don't see in dimension 1. Then there's an interesting result of Daskalopoulos, Hamilton, Lee. And they proved this very important result, that the concavity, not of U, but of the square root of U, is preserved by the porous medium equation. So what they show is, and your initial data has the property that the square root of U is concave, and it has some regularity. And they also assume a non-degeneracy condition, which means it initially moves at time 0. Assuming that, then at later times, the square root of U will also be concave. Another way of saying that is we say that 1/2 concavity is preserved. So let me just give a definition here. So this is commonly used, that we say that a function is alpha concave. It means that U to the alpha is concave. So the square root of U being concave, we say is 1/2 concave. U being concave is just 1 concave. And then we say that log U being concave, we call that 0 concavity. So just some terminology. So Vasquez, in his monograph on the porous medium equation in 2007, he asked the question, is concavity preserved in higher dimensions? It still wasn't known. There was a partial result by Ishige and Solani who showed that alpha concavity is not preserved for some non-explicit but small alpha positive. And then I want to describe our main result, just appeared this year. So we produced examples in dimension n equals 2, such that for any alpha which is not equal to 1/2, between 0 and 1, we show that alpha concavity of U is not in general preserved for solutions of the porous medium equation. So let me say a little bit more about this. So in particular, this says that the answer to Vasquez's question is no. When alpha is 1, our examples show that no, indeed, concavity is not preserved. So our examples were for n equals 2. Shen, Thaler extended our methods to higher dimensions, so you can come up with examples in any dimension. Just a reminder, again, we're assuming this m equals 2. If you wanted to assume just general m, then you'd be talking about concavity of the pressure, U to the m minus 1, not concavity of U itself. So in fact, we show two things. So we show the first thing we show is that you can break concavity. Well, we show you can break concavity in 2 possible ways. The first is that you have something called interior concavity breaking, which is just, by that I just mean that you can lose your alpha concavity in the interior of the support. The second thing we show is that you can get boundary convexity breaking, and this happens when alpha is between 0 and 1/2. On the other hand, we show that second boundary convexity breaking cannot occur when you're in that range alpha between 1/2 and 1. So our results are optimal in this sense. So we have 2 types of convexity breaking. Yeah. Oh, yeah. Yeah, the question is, if m is not 2, are you looking at different alpha? No, it does not affect the alpha. The alpha are the same. And in fact, the methods are very similar. It really, as I said, our results are really quite insensitive to the particular value of m. So let me go a bit more precisely into what it is that we actually show. So the first thing we show, as I said, is this interior concavity breaking, and it occurs whenever alpha is not equal to 1/2, but in that range 0 to 1. And what we do is we construct an example. It's relatively simple. I'll explain later. It's a smooth function on the closure of the unit ball in R2. And this U naught has the property that it's alpha concave on that unit ball. It's positive on the interior of the ball, and 0 on the boundary of the ball. So the support of U naught is just the ball itself, or this capital omega T is the ball itself. And I assume it has this, we show it has this non-degeneracy condition as well. That's not really that essential. And what we show is that initially your U naught to the alpha is concave, but then it loses concavity somewhere in the, well, in fact, in the neighborhood of the origin. And so you get this kind of behavior so that U is not going to be alpha concave in the neighborhood of the origin for T between 0 and delta. The second thing we show is the so-called boundary convexity breaking. So in this case, we have to restrict to alpha being between 0 and a half. And what we do is we construct a set, capital omega naught, convex set in R2, whose boundary is smooth. It's a bounded set. And we construct an initial data, U naught, which is smooth on the closure of omega naught, and it's going to be alpha concave. And it's going to be positive on omega naught, 0 on the boundary, so on the boundary. And again, it's non-degenerate, which just means that it starts moving immediately. And such that, so here's your initial omega naught, and these arrows are showing how the boundary is moving in time initially. And it's moving more on the left and the right than it is at the origin. And that means that at some later time, you get this kind of bean shape, which breaks the convexity. I want to explain why it is that actually this boundary convexity breaking only occurs between alpha between 0 and a half. Okay, and then we show it's not convex. Okay, so let me make a remark. So as I said, these results are optimal by this work of Daskalopoulos, Hamilton, Lee, who showed that half concavity is preserved. So why can't this boundary convexity breaking occur when alpha is in this range 1/2 and 1? And the reason is very simple. Suppose your initial data is alpha concave between 1/2 and 1, well, that implies that actually U naught is 1/2 concave. So it's a fact that if you're alpha concave and beta is less than alpha, then you're beta concave. And this is a straightforward computation. Here, for some reason, I replace U naught with V, so for V, U naught. So being alpha concave just means you take V out, V to the alpha, and look at its Hessian. I want that to be less than or equal to 0. So when you compute that, you get this expression. On the other hand, if you pull out a factor of alpha V to the alpha minus 1, you get simply Vij minus 1 minus alpha Vi Vj over V. And I can rewrite this as two terms, since you get the minus a half and another minus a half and then the plus alpha. And you see that this is positive definite as a matrix. And therefore, this thing being less than or equal to 0 is stronger than this thing being less than or equal to 0. But this thing being less than or equal to 0 is precisely that U naught is a half concave. Here again, I'm writing V for U naught. But on the other hand, this result of Daskalopoulos Hamilton Lee shows that for later times, this will be half concave, the solution. But then that means that the set where there is gas, this capital omega T, that's going to be convex. And that's because if you take any concave function, then the set where it's positive has to be convex. And so that's going to be true for U to the 1/2, and therefore it'll be true for U as well. Okay, so you can't have convexity breaking for alpha between 1/2 and 1, and that shows why our result is optimal. Okay, so that's the results in the case of the porous medium equation, and I want to move on and talk a little bit about the Stefan problem. And this is a problem of melting ice. So there are different versions of the Stefan problem with increasing complexity. I'm going to take the simplest possible case. You take some capital omega T's in a nice domain. I've drawn it convex, but it just doesn't have to be convex. And we have U, a function U, which is going to satisfy ut equals Laplacian of U on this set capital omega T, which is the set where U is going to be positive, and U is 0 on the boundary. And so I'm going to think of the outer part as being the ice, which is kept at temperature 0, and the omega T as being the area where you have warm water. And the idea is that the warm water is going to melt the ice over time. So what happens is that, so this omega t is going to expand. It's going to move in the direction of the ice. And how is it going to move? Well, you see that this temperature is 0 on the boundary. What matters is the gradient of the temperature. And the larger the gradient, the faster you're going to move and melt the ice. And the model is that the boundary of omega t moves in the normal direction with speed, the absolute value of the gradient of u. So our result, again, joint with Albert from a couple of years ago, says the following, that similar to our result for the porous medium equation, we get that alpha concavity is not preserved for the Stefan problem, where alpha is between 0 and 1/2. So in particular, it says that log concavity for the Stefan problem is not preserved, and this is in sharp contrast to the heat equation. So remember my first slide, I said that for the heat equation, log concavity is preserved on Rn. In fact, log concavity is preserved whenever you have a Dirichlet problem on a convex domain. So you have u is 0 on the boundary. It's also true that log concavity is preserved. What we see is that for the Stefan problem, that's not the case. And this is actually with some surprise. The actual example we come up with is very similar to the one we had for the porous medium equation. There's some minor technical differences, but the domain we construct is the same. And what we see is that we get it at t equals 0. It has this, it's a convex shape, but then at any positive time for t between 0 and delta, some small delta, it becomes this sort of bean shape that loses its convexity. So I said that we use basically the same example. So I want to explain why is there this connection between the Stefan problem and the porous medium equation. So if you recall from the last slide, the Stefan problem is solving the heat equation in this domain, and the boundary moves with the speed gradient of u. On the other hand, the porous medium equation, you don't specify how the boundary is moving, but it comes from the equation. I want to explain that now. So that's the equation for the porous medium equation. So how does the boundary move in the porous medium equation? So this is a simple calculation. I'm just going to assume we have enough regularity so that I can do a formal calculation, not worry about smoothness and so on. So suppose I have some point on the boundary of capital omega t. Let me call it x of t. And now I want to ask the question, well, how does x of t move in time? Since x is on the boundary and the u is 0, so u of x of t is just equal to 0, and therefore if I differentiate in time, just by the chain rule, I'm going to get the gradient of u dot dx dt plus ut is equal to 0. On the other hand, what is ut? Well, recall that the u satisfies the porous medium equation, and therefore this is equal to 2u Laplacian u plus twice the gradient of u squared. But on the other hand, u is 0 on the boundary, and therefore, assuming enough regularity, this thing is equal to 0. And so you're only left with this 2 gradient of u squared. But that implies then that dx dt, the only possibility is that dx dt has to be minus twice the gradient of u if x of t is moving normal to the boundary. So what we see is that the boundary of omega t is moving in this normal direction with speed twice the gradient of u. So this is some factor of 2, which in fact I forgot when I first wrote the slide. So we see that the Stefan problem, the PME, have this same feature that the boundary moves with the gradient of u. Okay, so I want to move on to my third example, which is rather different, and this is the so-called quasi-static droplet model. So here, I'm going to take a function which is the u of xt, and this is going to represent the height of a liquid droplet at a point x in Rn at some time t. And of course, since it's a height, it's going to be bigger than or equal to 0. Suppose it looks something like this. And the question is, well, how does that shape of the droplet change over time? So this is the model. Okay, so again, I'm going to write capital omega t for this set where u is positive. And I'm going to assume, as I did with the previous 2 examples, that I'm going to be working with sets where capital omega t bar is compact. So what is the model? So it's a very simple equation. Just the Laplacian of u is equal to a constant. This equation is also known as the torsion equation. So this holds on capital omega t, where u is positive. we have the capital of omega t is going to move at certain speed, and I'm going to write v for the speed at which it moves in the normal direction. And this is going to be some function capital F of the norm of the gradient of u, where capital F is some given function with the property that f prime is positive. I'll say a little bit more about the choice of capital F in a second. Here I'm going to allow f to take on negative values, and with that I interpret that if it's positive, you're moving outwards, and if it's negative, you're moving outwards. And then I have a normalization, which is the integral of dx equals 1. And so now you see why that lambda t, have this lambda t equals a constant, that y that depends on t. The idea is that given a domain capital omega t, I can always solve, say, minus Laplacian u equals 1, and then I can just scale it so that the volume is equal to 1, well, then that will change that constant. And so you get the constant lambda t depend on t, and it comes from that normalization. So the idea is that this is quasi-static. You'll notice that the equation for you, unlike the other examples, there's no du dt here. What you're doing is you're solving an elliptic equation for each time. So you have a domain, capital omega t, you solve for u, and then u tells you how the boundary is changing. So that's just saying that the last one is just saying that the total amount of liquid is preserved. So let me make a couple of remarks. So the physical models here, which I don't, I'm just reading it and I can't tell you anything more about it, but they take f of r to be r cubed minus 1 or r squared minus 1. And in particular, notice that these could be negative. So we are allowing f to be negative. It's very hard to come up with explicit solutions to this equation. I don't know of any non-trivial explicit solution. The stationary solutions are just going to be where omega is a ball and u is just quadratic. But on the other hand, if you take capital omega naught as any ellipse, then you can see that to solve this Laplacian u as a constant, you'll get that u naught is quadratic. And so you can easily see that when you have an ellipse like this, the gradient is going to be smaller at these sides and larger on the top and the bottom if you draw it like this. And so then this is going to want to go inwards and this is going to want to go outwards. And so you expect that that will converge to a ball. There's no explicit way to see this. Okay, so the capital omega t determine the solution. So it's unlike the previous case where you have really a function u and the value of the function is important. Here, once you have omega t, then you know the solution. So you can think of a solution to this problem as really just being a family of domains. For each domain, you then solve this equation minus Laplacian u equals constant. And that gives you the u, and that tells you how the domains are changing. But really, the domains omega t determine the solution. And then there's a natural question, which I've been asking before, and you can ask here. And then Feldman and Kim asked it in 2014, is convexity of capital omega t preserved in time for this equation? And I was, okay, so this again is the model, which I'm writing down. So our result, again, joint with Albert, appeared last year. And so we make this assumption on the capital F. It's a very mild assumption. I'll say a little bit about it later. Then we find an example where convexity is not preserved. So you immediately lose convexity. So you might hope that this liquid drop, that its footprint will, if it's convex initially, it will remain convex. It turns out that's not the case. So we find a bounded domain, convex domain with smooth boundary such that it just immediately breaks that convexity. So instantaneous convexity breaking. So let me make a couple of remarks about it. So in these cases, which I apparently are physically relevant, capital F is r squared minus 1 or r cubed minus 1, you can compute that limit is actually infinity because in the first case, the second derivative would just be 2 divided by f prime would be 2r, so it's just 1 over r. So that will be infinity, so that's certainly satisfied. So what's the idea of the proof? Well, we take the example, the starting point is an equilateral triangle. So it's a very, very simple idea. You take an equilateral triangle of side 2a, and it turns out, and we found this in a paper in the 80s, but I presume it's known before that, is that you can write down a solution explicitly, and it just turns out to be a cubic polynomial. And this is a solution to minus Laplacian u equals constant. And then we simply want to look, well, which direction, what does the gradient look like for this particular solution? And it turns out that it immediately breaks convexity. So this is the case of an equilateral triangle, which is not a domain with smooth boundary, but you can smooth out the corners and you can make it have smooth boundary. So no issue there. So it's not convexity positive. So the answer to the Feldman-Kim question is no, convexity is not preserved. Let me just say a word about the proof and where this condition about the limit comes in. So remember that we were assuming this condition on the limit. So you can write down this solution on the equilateral triangle, and I put a constant in front, and that constant is 5 over 3a to the 5. So this is an equilateral triangle where each side is 2a. And you choose that c. With that particular choice of c, it turns out that the integral of u dx is equal to 1. I guess it should be integral of u dx dy. And then you can compute u sub y, just take the partial derivative with respect to y, and you see that the only term you get is where the derivative lands here, and then you get a 3a squared, and you get a minus 3x squared, so you get this 3ca squared minus x squared. And then the speed, remember that the speed of the boundary, v, is moving like f of 3ca squared minus x squared. And then what I want to do is simply compute the second derivative of capital V. So very, very simple. And when you do that, you get two terms. Both derivatives land on the f, you get this term. Or when you do one derivative landing here, and then you get a minus 6cx, and the derivative lands here. But then you can choose the a to be very small, which makes the c very large. And if the c is large, then this term here can be larger. It can dominate this term times 1 over gamma, as long as x is large enough, say bigger than a over 2, for example. And then that implies that actually v prime prime is positive for x close to a. And the reason is that when x is close to a, this is close to 0. And then this f prime prime is going to be at least like gamma times this, and then it's going to this term is going to dominate this, and you actually get that this is strictly convex. But that's going to contradict. That's going to mean that you're going to immediately lose convexity. And the reason is that your speed is like this, and so in the middle your speed is very low, for example, and on the edges it's very high. So it means that you're when you convert it back to as you're moving outwards, you're moving more on the left and right than you are in the middle, and so you're going to lose convexity. Let me go back to say I want to say a little bit about the proof in the case of interior convexity breaking for the porous medium equation. So remember, we're taking the porous medium equation with m equals 2. This was ut equals Laplacian u squared. And what we proved is that when you take any alpha which is not equal to a half in the range 0 to 1, then you can get immediate interior concavity breaking. I'm going to assume here that I'm in this particular case where alpha is between 0 and a half, or alpha is 1, and the other cases you have to take a slightly different function. So the idea, again, is very simple. Of our example, you can you write down a fourth order polynomial, and this is the polynomial we take, where here a is a positive constant to be determined. And then one can check, this is a short calculation, that this d squared of w is negative, and therefore this is a strictly concave function away from the origin. On the other hand, w11, you can see you just get two terms here, but they both vanish at x1 and x2 equals 0. So w11 is 0, and so you don't get strict negativity of the Hessian at the origin. And then you define w equals u0 to the alpha, and that means that so u0 is going to be my initial data for the porous medium equation. So what I'm saying is that u0 to the alpha is then going to be concave. So my initial data u0 is alpha concave. And then I simply compute at the origin ddt of w11. And then what I want to claim is that this is going to be positive. And so this I claim is going to be positive if a is large. So there's some computation there where you have to look at the equation, evolution equation for the porous medium equation. So why is this positive if A is large? Well, if there's two cases we're looking at. If alpha is 1, then this vanishes, and you're only left with these. Alpha is 1, so you just take A to be bigger than 8, and then that's positive. The other case is when alpha is between 0 and 1/2, and in that case, this term dominates. Notice that this is positive because alpha is less than 1/2. This is positive, so this dominates because there's an A to the 4, and then you take A larger, and that's positive. But then you see that you can't possibly be concave if W1 is going to be positive at later times. So that says U alpha 1, 1 is positive, and therefore you're not alpha concave. Now this is a local, I've done this locally near the origin, but you can always extend that initial data to a unit ball in a way that it's still alpha concave, and you prove the result. The other proof I want to say something about is about the convexity breaking at the boundary. So there's two, so let me give just a brief sketch here. So let me first take the case when alpha is 0. This is the case of log concavity breaking. And assume that the boundary is moving with speed nabla u, so the magnitude of the gradient of u. So this occurs either in the case of the porous medium equation or in the case of the Stefan problem. So what we're going to do first of all, so I just want to give you the idea. This was our starting point. We constructed the data on the upper half plane. So look at capital omega naught to be x2 bigger than 0. Of course, eventually we want to construct an omega naught which is convex and bounded. But let's start with something which is unbounded. And what we're going to do is we're going to show that this u initial data, this u we construct, is going to be log concave in the upper half plane, close to the origin. And we're going to use that as a starting point to construct the data on an actual convex bounded set omega naught. So what we do is we take this very simple function. Again, it's a polynomial of degree 4. And it's simply u is x1 squared x2 plus x1 to the 4x squared. And then one can compute the x2. When you put x2 as 0, you only get this term here, x1 squared, which tells you that the gradient of u along that line, the boundary line, is going to be x1 squared. So here's my picture. I have this omega naught, it's just the upper half plane, and I've written down a very simple function u, and it has the property that the gradient of u is x1 squared, but we know that the gradient is moving with speed, the gradient of u, so it looks like x1 squared. So it's not moving at the origin, it's moving more on the left and the right. And so what's going to happen? Well, it's going to stop being convex. It's going to break that convexity. And then one has to check that this particular solution is log concave near the origin. That's the first thing one has to do. And the second thing is you have to redefine it away from the origin, and you have to be able to do this in a convex set u naught, not in the upper half plane. But that's the basic idea. What about the case of so it's kind of interesting. Why does this half come in? This again has nothing to do with the porous medium equation. Why this half comes in? It only is simply something to do with the gradient function and concavity. So if I just go, so if I call what I took here, the example I took was just x2 times x1 squared and then x2 squared times x1 to the 4. Let's take something a bit more general than that. Let's take x2 times some function f plus x2 squared times some function f squared over 2. And again, I'll take it on the upper half plane. And here we want to see where it is that this 1/2 plays a role. This alpha equals 1/2 turns out to be the borderline case. And as I said, there's nothing to do with the porous medium equation. It's just a result about concavity. So let's do some calculation. Well, I can do this all very explicitly. Just differentiate with respect to x1. And we get this term u1 is equal to x2 f prime plus x2 squared f prime. Differentiate with respect to x2, and you get f plus x2 f squared. And so that tells me that when you're on the boundary of this set of an x2 equals 0, it goes away, you just get f. And of course, the u1 will just be 0 there. So the gradient is just equal to f. And then what I'm going to do is I'm going to construct my f so that my f is convex, so that will break the convexity. Let's do some more computation. So what's u11? So differentiate again with respect to x1. I get this term here. You get two terms here when the derivative lands here. Differentiate this with respect to x1 prime plus x2 and then 2f prime. And then u22, you just get the term f squared. And now what do we want to do? So we want to construct my f. So I want to construct, remember f is unknown. I want to construct it so that u to the alpha is concave on the upper half plane. And remember that being alpha concave just is saying that this 2 by 2 matrix is going to be on R2. So this 2 by 2 matrix has to be negative definite. So I want to show that. Well, we'll just compute. And then what I'm going to do is just ignore the higher order terms in x2. I want to do everything near the origin. And I claim that you can always extend. So I want to do this near the origin. And so when I compute u11, you see when I do u11, the lowest order term is just f prime prime, this. And then from the u1 squared, you just get this f prime squared. And then when you do the same with the u22, you see that the u22 gives you something which is of order of x2, but the u2 squared will give you an f squared. So I just get this. And you notice that this is negative. I want this to be negative as well. So for this to be negative, I'm going to need the f prime. I'm going to need this f prime to be relatively large compared to the f double prime. And f will have to be positive, otherwise it won't. U wouldn't be positive. And then finally, this u12. So you get some x2. So you get this u times u12. So I get this term, and then minus u1, u2. I get this f prime, and then the f. And then you notice you can simplify this a little bit. Some canceling, you just get alpha x2 f prime. And so all we need to do, so I want to show these two are negative, and I want to show that I want the determinant to be positive. So what's the determinant of this 2 by 2 matrix? Well, I get simple calculation. You compute this. So let's see. You get this term here, ignoring these higher order terms times this. And what do we get? So you get this 1 minus alpha squared times f squared f prime squared. But then you get minus alpha squared. So you get the 1 minus alpha squared minus alpha squared. You get this 1 minus 2 alpha, and this is the key term. And then on the other hand, here you get, from here, you get this minus 1 minus alpha f cubed f prime. So what do we want? Well, what we want to do is choose f to be convex, and we want to choose f prime to be large. And the reason is that we want this to be positive. We want the determinant to be positive. The only way that this determinant can be positive, if f prime prime is positive, is if alpha is less than 1/2, and that's where this comes from. And then I can always choose my function so that f is large, f is positive, f prime can be large enough so that this term is larger than this one is positive. And so you construct this solution where f is convex, and it's going to immediately break the convexity. And then this is my last slide. So, so what have we seen? Well, what we've seen is that in general, preservation of convexity and concavity for these free boundary problems that I've been talking about is fairly rare. And we saw an example of this Daskalopoulos, Hamilton, and Lee. We don't see it in the Stefan problem. We're not seeing it in this quasi-static droplet problem. Why do we care? We care about convexity. Well, something that's very useful about it is that if we have, it gives us some sufficient condition so that we can have solutions which don't have singularities which are too bad. And something that can happen where you have free boundary problems is that the boundary can intersect itself. And so suppose we want to come up with nice solutions which don't have this very bad behavior. Well, one thing we could do is insist that the initial data is convex and it remains convex, and then we don't have the boundary coming in and hitting itself. Interesting question which people ask me is, well, what is the significance of this 1/2? So for the porous medium equation, why does 1/2 play this important role? We saw in the last slide, there's something about 1/2 which is just to do with concavity and the gradient, which has nothing to do with the porous medium equation. But I don't have really a physical reason why it is that half concavity should be preserved by the porous medium equation. Like why there's some maximum principal argument that they use Daskalopoulos Hamilton. It just happens to occur at when alpha equals 1/2. It'd be interesting to know if there are other examples for other free boundary evolution equations. And then what about if you replace convexity with something else? Maybe there's some other kind of geometric property that you can come up with which could be preserved. So for example, something like star shapeness, if that were preserved, then that would also rule out these kind of singularities where the boundary hits itself. So there's lots of, I think, interesting questions to ask. I'll finish there. Thank you.
Is there any question or comments?
Hi, Ben. What about space forms or whether the curvature would affect the power?
Yeah, that's an interesting question. If you think about the porous medium equation, but on a space, yeah, I haven't thought about it, but that's a good question to ask, actually. Yeah, may well affect it.
Suppose we have, say, floats and couple. Right now, the metric is fixed. Couple with the pitching low and porous medium.
I've never thought about that. The coupling equations. It's different.
Well, in that case, there are works, almost actually improve the version of the Yao Hamilton type without this couple. Needed fixed dimensions. So any
I see. Okay, yeah. So there's this Aronson Benelin or something like that inequality. I see. And you're taking a close, so probably you don't have any boundary in that case. Well, you could.
So might be some issue, but
Yeah, I see.
space forms
That would be interesting. Yeah.
the half big could be shifted by code.
Yeah, may well be the case. Yeah, interesting question.
A remark and question. The remark is that it seems to me that the convexity breaking is Stefan problem of the boundary is an old result. I heard about it maybe 30 years ago. Not the alpha concavity, but the convexity breaking. My question is about your first point here. Finally, your proofs are very explicit and very constructive. Your proofs, convexity breaking. Don't you think that the preservation of convexity is actually generic in the sense that for most initial data, for example, you will have preservation?
Oh, I see. For most initial data, which is alpha concave, that you would have breaking. I don't know. Yeah, I don't. I'm not sure if I would think that it was, but I don't have a feeling of it. I never thought about that. Yeah, we just wanted to come up with one example.
Yeah. No. Like the Stefan. Then you have this preservation, and also preservation is not.
Oh, is that so?
Yeah.
Oh, okay.
And then, yeah, maybe the 1/2 percent. So if they that's Stefan, you would modify it by, but instead of that, you could move by the gradient, take the power of that gradient. So we then maybe have special points. Yeah, might have a special power where what happens.
Okay. Yeah, that's interesting. Yeah, if you modify the problem, take some other function of the gradient. Yeah, that's possible because certainly with the Stefan problem, you're not going to get this problem of interior concavity breaking for the log concavity because we know that that's going to be preserved for the heat equation. So yeah, that's a good question. Good idea. Good idea to try. Thanks.
Hi. Does your argument apply to other dimensions? You mentioned that the case for n larger than or equal to 3 is proved after your work, right? So for
Yeah.
other problems, and does the argument the same to you?
I don't think there's anything special about n equals 2 versus higher dimensions, so I expect that you can come up with examples in all dimensions, but once we found an example in dimension 2, that was enough.
Okay, if there is no more question, let's thank our speaker again.